Hello, welcome to our talk. I'm Chen Yuzhang.
I am Dominic Winteron.
Today we will together introduce semantic fusion, a novel testing approach, and how we use it to validate SMT solvers. This work was performed with Zheng Dongshu. Let's start with a brief introduction of SMT problem. Given a first-order logic formula phi, for example, x greater than 0 and x less than 0, the SMT problem is to answer whether we could find an assignment for the variables in the formulas that makes the formula become true. If we find such an assignment, the formula is satisfiable. For this formula phi, since we cannot find an assignment for x that makes phi become true, phi is unsatisfiable. But if we change the last 0 to 1, the new formula is satisfiable. Since x equals to 0.5 is a satisfying assignment. SMT solver is a tool for solving the SMT problem automatically. Given a formula phi, an SMT solver will report the satisfiability of the formula. For example, for this satisfiable formula, SMT solver reports set. In fact, many programming language-related techniques depend on SMT solvers. For example, symbolic execution, solver-added programming, program verification, static analysis, program synthesis, and so on. However, for an set formula, if SMT solver reports unset, there should be a critical soundness bug in SMT solver. Since many applications depend on SMT solvers, if there's some critical soundness bug in SMT solvers, client software of the SMT solvers would be unreliable. Thus, testing SMT solvers is crucial. However, testing SMT solver is challenging. First, there are two challenges: how to generate test formulas and how to obtain the test oracles. Let's see this example. It's a screenshot of an SMT formula. The typical formulas are usually large and complex, so it's hard to manually design such test inputs for SMT solver. And it's also hard to decide whether the result of the solver is correct or not. And most importantly, it's challenging to find bugs. In fact, before this work, almost all critical SMT solver bugs in Z3 and CVC4 has been uncovered directly by their client applications. To address these challenges, we proposed Semantic Fusion, which can generate large number of test inputs with known satisfiability. And in our 4-month evaluation, it found 46 confirmed bugs in Z3 and CVC4 default mode, and 42 out of which has been fixed by the developers. The core idea of semantic fusion is to combining the structures of two seed formulas into a new formula, and make the connections between two subformulas while preserving the satisfiability. Let's explain semantic fusion with a simple example. Given two satisfiable formulas that do not share variables, semantic fusion first concatenated them by formula conjunction. The concatenated formula is also satisfiable by construction, since there is an assignment for x and y to satisfy the formula. Now we attempt to use a new variable z to build the connection between two subformulas. First, we let z equals to x plus y. This function is called fusion function. Then, according to the fusion function, we invert the fusion function to x and y respectively. These two functions are called inversion functions. Next, we use the inversion functions to substitute some occurrences of x and y. For example, the second x and the first y. The fused formula is also satisfiable, since for an arbitrary assignment for the satisfiable concatenated formula, we can assign new variable z to the value of x plus y and keep the assignment for x and y. Then the model satisfies the fused formula. Let's see a real example. Given two satisfiable formulas that are written in SMT lib language, we use some colors here to make the process visible. We first concatenate them together. Randomly select some occurrences of variable x and y. Create a new variable z. Construct a fusion function z equals to x times y. Substitute the selected occurrences with the inversion functions. The formula should be satisfiable by construction. However, CVC4 reports unset on this satisfiable formula, which means a critical soundness bug is uncovered by this formula. We reported this bug to CVC4 bugs tracker and it has been fixed by the developers. Fusing two unset formulas is similar to fusing two set formulas. For example, given two unset formulas that also do not share variables, we first concatenate them with disjunctions. The concatenated formula is also unset since the disjunction of two unset formulas with disjoint variables is unset. Then we also build the connection between two subformulas with new variable z and fusion function z equals to x plus y. Then we get the inversion functions and substitute some occurrences of x and y with inversion functions. However, after substitutions, the fused formula becomes set, which does not preserve the unsatisfiability of the seed formulas. It is because we can find an assignment, for example, x and y equal to 2, z equals to 0, which satisfies the formula. The root cause is the value of z minus y and z minus x can be different from x and y respectively, which breaks the unsatisfiability of the formula. So for the unset fusion, we have to add additional fusion constraint to the formula, which reflects the fusion relation between z, x, and y, to preserve the unsatisfiability of the formula. Here is a real example of the unset fusion. For two unset formulas, we concatenate them together. Select some occurrences of the variables. Introduce a new variable z and a fusion function z equals to x times y. Substitute the selected occurrences with inversion functions. Add the fusion constraint since it's unset fusion. Although not needed conceptually, we also added the inversion constraint to account for the specific semantic of division in SMT lib language. The fused formula is still unset. However, this reports set for this formula, which means the formula uncovers a soundness bug in Z3. We reported this bug to Z3 bug tracker and it has been fixed. Here are some demonstrative fusion functions and inversion functions on int, real, and string logic. Then we let Dominic introduce our experience on hunting bugs in two state-of-the-art SMT solvers, Z3 and CVC4. Dominic.
Thank you, Changyi. I next present the empirical evaluation of the semantic fusion methodology. We realized semantic fusion in a tool Yin Yang with which we tested the two state-of-the-art SMT servers C3 and CVC4. We did this from July to October in 2019. Once we found a bug, we reduced it with the C-code reduction tool cReduce and reported the reduced cases on the respective issue trackers of C3 and CVC4. Let us have a look at the results. In total, we reported 58 bugs, 45 in Z3 and 13 in CVC4. Out of these, 46 were confirmed and 42 got fixed by the developers. At this point, we would really like to thank the Z3 and CVC4 developers for their incredible support in addressing our issues and in fixing our bugs. Among the 46 confirmed bugs, 30 were soundness bugs, where the SMT solver gives an incorrect result. Soundness bugs are the most severe bugs in SMT solvers. We also found a couple of crash, performance, and unknown bugs that we consider the byproducts of our fuzzing campaign. Most bugs in Z3 were found in string logics and nonlinear logics. Most bugs in CVC4 were found in string logics. A natural question to ask is how significant are these findings? To investigate this, we have done a study on publicly reported soundness bugs in Z3 and CVC4. For example, in 2017 there were 22 soundness bug reports in Z3, while just a single bug report in CVC4. By comparison, Yin Yang has found 24 in Z3 and 5 soundness bugs in CVC4 during only 4 months. It found more than 2/3 of all ever found soundness bugs in nonlinear logics in Z3 and more than 1/3 of all string soundness bugs. As another way of investigating the significance of our findings, we looked at historical Z3 and CVC4 releases. 9 bugs affected the 4.5.0 release of Z3, which is more than 3.5 years old. 2 of our soundness bugs affected CVC4's 1.5 release, which is 1.5 plus years old. Altogether, this shows that Yin Yang's findings included soundness bugs that were missed by previous approaches, and also by the extensive regression test suites of the solvers. Yin Yang has found long-standing soundness bugs. Another important research question is whether semantic fusion is necessary to find these bugs. Or stated differently, could we have found these bugs with a simpler approach? We examined this question by removing the variable fusion part from Yin Yang, which results in an approach that we call concat-fuzz. Concat-fuzz conjoins satisfiable formulas and disjoins unsatisfiable formulas, and we then tried to retrigger the bugs found by Yin Yang with concat-fuzz. As it turns out, it's only possible in 5 out of 50 cases. As another experiment, we looked at the code coverage difference of concat-fuzz and Yin Yang. The results show a noticeable improvement in code coverage. Notably, the difference in line coverage already translates to 2,800 additional lines covered in Z3, 480 in CVC4, due to the sizable code bases of Z3 and CVC4. So Yin Yang can consistently achieve higher code coverage than concat-fuzz, and together with our last experience, this shows the necessity of semantic fusion for bug finding. Let us now have a look at some bug samples. The first one is a bug in Z3's real arithmetic. The formula is unsatisfiable, and so CVC4 correctly reports unset on this formula. However, Z3 returns sat, which is unsound. Z3's main developer thanked us for this report and fixed this bug promptly. Here's a bug in CVC4's integer arithmetic. The formula is very simple. It basically asks whether there are 2 integers whose division results in -1. Clearly, the answer is yes, and the SMT solvers should give set on this formula. However, CVC4 reports unset on it, which is unsound. A CVC4 developer labeled this bug as major, which underlines its importance. This one is a bug in Z3's string logic. The formula is unsatisfiable, which the legacy Z3 4.8.7 correctly detects. However, the Z3 trunk version returns set on this formula. Z3's main developer fixed this bug promptly. He said that this bug exposed an incomplete axiomatization of the string to int function and gives rise to rewriting opportunities in strings. Another string bug, this time in CVC4. The shown formula is unset, which Z3 correctly detects. However, CVC4 returns set on this formula. One of the CVC4 developers commented this bug by another excellent find, thanks a lot. And he also labeled it as a major. Another soundness bug in Z3. Interestingly, the unreduced formula of this one has triggered a bug in both solvers at the same time. The formula is unset, but both solvers return set. So as a short summary of this presentation, SMT solvers are the basis of many PL technologies, and testing SMT solvers automatically is challenging. We have addressed these challenges by designing semantic fusion, whose key idea is to fuse formula pairs and feed the fused formulas to SMT solvers as test seed. Our practical realization of semantic fusion Yin Yang has found many bugs in the state-of-the-art SMT solvers Z3 and CVC4. Last but not least, we would like to announce that we will release Yin Yang on GitHub by the end of this summer. Please stay tuned. Also check out our websites for statistics and the bug report links. Thank you for your attention.